Now I can do the playback. So, so this is a small example, a real life example. It's a PDZ domain mediated protein. It doesn't matter, something from biology. I mean, perhaps some of you know much more about this than I do. So here it's a classical representation. The thicker the edge, the bigger the curvature in absolute value, the bigger the node. And there is a code color like in graphics or in imaging. Red means negative. Here blue is positive. And you can see that most, as I said, most edges and nodes have negative curvature. This is a combinatorial network. And as I told you during coffee break, at that point in time, there were very few decent examples, real life examples with anything but combinatorial weights. Okay, so that's one. The other one, hey, huh? Now this doesn't work. Sorry. So okay, I can always do that. Okay. So this one, it's convenient. Sorry. So this one is a Euro. It works for you. For me, no. Yes. Okay. So just my luck. So this is a Euro road networks, and as you can see, it's the same convention, and you learn something from this. For instance, not all roads go to Rome anymore. And for some reason, Yaroslav is more important than Rome, or I don't know what. Madrid, by the way. I don't know why. An edge is a road. Autobahn, whatever, I don't know. No, it's not a direct one. There is one from Moscow to Brno. And I didn't build the graph. I only sell it to you, repackage it. So these two results are with Arigid, of course, with Jürgen. And this one is one of the first papers with Melanie Weber. And here we have a peer-to-peer network. And again, you can see that this is a peer-to-peer network. This is a heat diagram. So this is a node. This is a node. You have a pixel if there is an edge between them, and you paint them by the color of the intensity of the curvature. It's not very illustrative here, but here is important because you can see that. So histograms are a very important thing. This is something as a mathematician I would never have guessed. But this, and actually I learned that, and not from my experience in electrical engineering and imaging, but Jürgen, people in biology use them a lot, it turns out. So this is a histogram of degrees, and this is a histogram of Forman curvature, and you can see they're very different. They're not just scaled up versions. You have this hump here. It's very different. So it suggests these are different notions. Okay, so then we had, again, so Arigid, whose field is mainly biology, said, no, we have to convince people it's good for something. As a mathematician, you don't have to do that to me. Of course, it's true. There is a theorem proving it, yes? But for biologists, it's important to really sell the stuff, to convince them. So we wanted to see that curvature and degree are different. So you can see there is no correlation, basically. This is for real-life networks. And here we did something for, okay, yes. And there we have something with, versus a clustering coefficient. Why? Because clustering coefficient is well known. It's also a discrete curvature for nodes, so it is natural to compare. So there is, again, no correlation. Basically, here the comparison was done with these classical models, Erdősény, Watts, Strogatz, and Barabasi, Albert. And so again, there's something you have to convince people, at least in complex networks, that you can do as well as they do. And here is the same thing, but for the real life networks, that's just so. I won't go into the details because by now I don't remember them as much. And it's kind of, it's relevant, but it's important there is no correlation. It's a different measure. And then we wanted to show more invariance, to compare with more invariance. And we deal with betweenness, which is important. And of course, from a mathematical viewpoint, it's nonsensical because betweenness is a global invariant, whereas these curvatures are locals. But again, since you try to sell it to a different type of population, it's important to understand their culture as well. Okay, so again, it's a negative correlation, so very different. Again, for real life networks and so on and so forth. And there is another thing that is robustness. So you try and remove, you want to understand how important an edge is to see how fast your graph disintegrates if you remove edges. So you can see that in most cases, Forman curvature outperforms the other measures, so at least as well. The same for real life networks. So in real life networks, it's even it's the best, I would say. Okay, so you asked me about in and out degrees. Okay, I think you too, yes? So here is the notion. You have a notion of outgoing vertex Forman curvature, a notion of ingoing Forman curvature, and you have two versions. So and then you can take their difference, whatever, and that is a measure of flow, how much flow goes through an edge. So Forman curvature, at least this discrete version, is a measure of flow through an edge. And that's why I think it's good for. Sorry? Here, yes, it is for a node, but you can, yes, sure, sorry. The basic one is for an edge. And this is another thing which we did with Melanie. It's a nicer picture. It's a web graph. It's a Google one. And it's directed, as you can see. How you can, if it's a heat map, how can you know it's directed? Because it's not symmetric. So that's how it looks. So that's what it could do then with R. Melanie used R, and it gives beautiful pictures, but it's very slow somehow. We'll come back to it in a jiffy. Okay, so this, I just came back to it. This is the same graph. You can see these are some very heavy nodes. And then you have some isolated clusters. And you can see it's oriented. You can see the arrows even here at some points. And you can see there are nodes which are connected by multiple edges. So it's a multi-graph if you look at that way. And the reason is very simple. So if you have a page which connects, to take an example from a very popular recent movie, if you take a page of Oppenheimer and then you have a lot of things taking you to the atomic bomb, the other way around. Yes. So that's how it looks like. So I don't know if I can do it here, but if it's actually, if you go zoom in, you can see much more of it. It's kind of a nice picture. So that's 1,000 nodes. Okay, so now I'm going back to the heat maps, and you can see how good they are. And so these are the heat maps of the social network we use, the web graph, and the biological network of some size. And these are for the Erdős-Renyi, Watts-Strogatz, and Albert Barabashi models for the same size, yes? Which are models so you can build them. And you can see there is no resemblance between real-life networks and these models. They are very far, quite far. Okay, so we'll see this a bit more in a second, if I remember correctly. So you can see even more the difference in these histograms. Yes?
Could you explain the paragraph underneath the comparison? Because maybe it's because I have an untrained eye, but I don't see why it's not resembling.
I tell you why, because I think you can see here, I forgot also. It's as Dumas-Père once asked about what happened to a character, he said, I can't remember. So the other guy said, didn't you write the novel? Yes, of course, but it doesn't mean that I read it, yes? So it happens along way ago. But you can see in this example, the biological, you have something here which you don't have in either of Erdős-Rényi or Watt-Strogatz. We have these small blocks around the diagonal, which you have here. This is a kind of phenomenon, which I might say, but it's easier to see it in the histogram distribution. I try to convince myself that I'm right. So you can see that the Erdős-Rényi and Watt-Strogatz have this Gaussian distribution for histograms, probabilistic, because they're built like that. Whereas Albert Barabas, it's a bit more close to the biological and social networks. Whereas the web graph, which is man-made, basically it looks somewhere in between, I would say. Okay. So, okay. So I don't know if I want to do this. I'd like not to use all my time for the basic stuff, so I just go very fast. So if there will be questions, then we have some time for that. I'm sorry, I want to show you some nice things also, not just basic examples. So it turns out that comparing histograms by look is very instructive. It's very useful. Okay. No, I didn't quite identify the source. To me, it sounded like a very old, deep, and depressed phone, but okay. So it's clear. I mean, you look at this and you look at this, you don't need further. But if you want to be precise, then you want a measure. I mean, I'm talking about measure like people from biology or social sciences and not like a mathematician. So you want a distance, basically. So you can really compute the distance between these histograms using convolution, using a kernel estimator, this Huygens idea, and then you can discretize it and go back to the Wasserstein distance and W1 and comparing them. And then you can do, it's useful. You can do a bit more. So you even can compare distances between pairs of either between a given real-life network and the model ones, or between the real-life networks themselves. And usually these distances tend to be smaller, I think. So that's possible. Here is kind of more to prove that you can. We did something, we really used it in a paper on textures, but much later on. Perhaps in the end I can go to it, but I don't. Anyhow, so if you remember, I started by talking about Forman. Olivier, yes? So we have at least two kinds of curvature, Olivier Ricci and Forman Ricci, and there must be, or should be, some connection between them because they are discretization of the same notion. And of course, they are very different in approach. And it turns out that, yes, they are very, very well correlated one with another, both for model networks and for real-life networks. So and that's, but in practice, it's much easier to compute Forman. And so there are people who have a paper who say that Forman curvature is a proxy for Olivier. I don't know. I don't like it that much, but yes, it can be used for that as well. Although it's a very, very different approach. So the question is, why should these two very different things give basically the same result? The answer, my answer, is because they are both very good in discretization, mathematical discretization, coarse curvature notions, which basically discretize, model the same continuous phenomenon. So they should give something similar. And there is a paper of Florentin Munch, I mentioned his name, I think, earlier in our discussion, and Jürgen, and and perhaps there is somebody else, and they show that, in fact, you can recover up to some, of course, then it's mathematics. You have to put in some axioms, extra axioms, and there is a strong connection. If you put enough quadrangles, then you get from Forman to Olivier. But that, of course, you have to decide whom to put in, then why. Yes. So this, but there is a strong connection between them. theoretical as well as practical. And I think here the practical one is the name of the game. Oh, sorry.
So, since the right x-axis in the function,
Okay, so it's the same.
it's just like the x-axis Forman and y have results.
Yes, now we have Forman on this axis
But one
and Olivier on this axis.
two
Yes, the curvature of the same graph. And you see, this is a correlation. So you see it's almost linear, yes? Or almost. Well, I don't know. Here it's almost.
Yeah.
It's statistics. So of course it's a lot of lying, but it's acceptable lying. Okay, so this is for the edges. So this is for nodes, this is for edges. Okay, so now let's go back to some nicer images and let's see what we can learn from these curvatures, and it's from Forman, and we learn a lot. So please, we have 4 examples here. 2 biological ones upstairs, a gene expression and a brain network, fMRI. That's why I asked. And 2 real life man-made. So this is a Google web graph you saw earlier. And this is, well, it's kind of web-made. It's a word co-occurrence in a text, where 2 words fit together. They did this for Balzac words, they did this for the words in the Bible. So there's something that goes a lot in the field. I'm not an expert. And you can see there is a huge difference. So this has big clusters, and you have the ring of smaller degree nodes. Here you have only 2 big clusters and long range connections between them. But that is you look with attention. But if you don't want to look at the graph and instead you compare histograms, then you see a big difference between them. So real life networks, and this is something which we discovered in parallel with Mellon and with Arigid, display this double or multiple hump phenomenon. You see they have this, it's like a camel with schizophrenic camel. Whereas real life man-made networks do not display this. There's a much smoother, well, there's some noise. Don't forget this is very relatively small networks, so noise is visible, but they don't have humps. And there is an explanation. It turns out that real life networks capture that, for instance, in gene expression, you look for something. So you have the main expression of these genes that do something, but then you have the housekeeping genes which control the basic processes in a cell, for instance. And I'll show you something from brain networks as well. Okay. Whereas in real life, in man-made networks, you don't have something because they are made to do something by us. So they don't have this different strat of activity. So this is a MRI network. This one is, I told you that it was very, very big. It has millions of edges. You discard and you discard and you discard, and still you can see nothing. So I even have a small movie. Almost a movie, yes. You see? It's real data from fMRI. You see they have this multiple connection between regions speaking to each other. Okay. I won't pretend that I know anything about it. But there are 2 colors. Why are the 2 colors? The idea was you put somebody in a fMRI machine and they make them clap. So the main process was that of the motor cortex lighting up. But there is another color, the blue or violet, whatever. People have the bad tendency of looking at their hands when they clap. So the visual cortex is also activated. And indeed, when you look at the distribution, you see that. Okay, so this is a paper in the end we didn't publish because of the statistics, I don't know. But it gets a lot of citation by now. And the biologist who did this, she has another paper, I don't know, she's keeping it, where they show that looking at these distributions of Forman curvature can predict intelligence. So if you want, I can send you a link to it. Okay, so they are good for something. Okay, more. So now I'll skip and I'll make some advertisements for my collaborators. There is something I think older with Olivier, but we did it with Arijit and Jürgen and Arijit's biological friends. You can say something about to understand autism and with comparison with other with healthy or normal or standard brains. I don't know how it's polite to say, and also with compared to other problems. Yes. This is not very new. The first papers on the geometry of the brain go back at least 40 years, and they could distinguish, detect epilepsy by the shape from the region in the temporal lobe. This visual, not fMRI. Yes, MRI, not fMRI. So we have some nice results here. There are some very nice results, I think, and it's a pity because this you can, if you put it, look at the paper, this you can zoom in and zoom out. This is a market prediction, crashes in the markets. We did it with Olivier. We did this with two flavors of Forman and another type of curvature. And you have these triangulation points. When before a crash, we have big networks and financial network. At some point, there is a crash in the market, and then that brings to a strangulation point, something like that. Bottleneck, and then you can see that. Yeah.
How did you turn the time series?
Mm.
And the graphs.
There are some, you look at some correlations between time series, and then you put an edge if the correlation is strong enough, something like that. No, it's not static. It's supposed not to be static. But of course, when we say predicting, you can look at the time and you say, just before the crash, curvature goes very negative. Stuff like that.
I thought the bottom part is also origin.
No. I can tell you more about. Okay, if you look at a bit of it, you'll see why it's good to go to higher dimensions. Okay. But this deserves a special talk, I don't know. And this is something, they have two, we talked about the guns, and this is one, I'm illustrating here, it's not the real run. Somebody else did something with Forman curvature on this kind of networks, like here, but we used it with Antamono and other people from the Imperial College to talk about yes, bottlenecks. Yes, but again, I'm not getting into it. I'm just showing, and this is an example from medical imaging. These are the ossicles in the human brain, in the human ear. They're very, very small. So if you want to detect them or to use mathematical computer methods for them, it's very hard. So it was an obstacle. So this is putting a layer of Ricci curvature on them, so to say, on the image, and gets much better results than classical methods like gradient and snakes, the so-called snakes. So why is this also important? Because Forman, these are very small bones. They have something like 200 voxels all in all. So if you try to use classical imaging models, which look smoothing of sorts, then you lose a lot of, you just lie. Whereas using the graph curvature here, it captures this segmentation aspect very well. It helps. But I'll talk perhaps about segmentation towards the end. Here, no, for in a deeper level. So of course, curvature detects contours, so you can use it for segmentation and for textures. So this is Forman one-dimensional, this is two-dimensional Forman. When you plumb in faces, so you can see this is negative, this can be positive, negative. It's a very good edge detector and also detects textures. This is a classical cameraman. Yes, it looks okay. And this is something else. We developed some kernels based on Bochner one, and for embedding, it's better separation. It was kind of natural. It's not the most important application, but it's kind of useful. Okay, so now when you have a Forman curvature, when you have Ricci curvature, mention the word Ricci curvature, you cannot say Ricci flow. Why? Because nobody cared about Ricci curvature. It was in the middle of the advanced course in Riemann geometry, and nobody really cared for it. But after Perelman solved the Poincare conjecture, basically with that, then of course everybody knew about the flow. And that's the idea. The flow evolves according to Ricci, the surface evolves according to the speed proportional to the curvature. For surfaces, Gaussian curvature and Ricci curvature are basically the same. So you can see that these fingers evolve much faster and become rounder, whereas these regions of negative curvature evolve slower and become flatter. Okay, so that's what happens. And and the higher the curvature, the faster it evolves. So in the end, it goes to a round ball. In the end, so that's something that happens. In the end, it degenerates to a round ball, and then it disappears in the classical setting. So I should say that Ricci flow, it's not our invention. It didn't start with us. The first discrete Ricci flow was developed by David Gu, with based on the words of Cho and Ro, which are very basic, based on circle packing. So for graphics, this is amazingly good. They use it also to embed networks. And there is a Olivier Ricci flow, again, done by many people. Alan and Jegao and David and others. And of course, it's natural to try to develop a Forman Ricci flow. So this is the way to do it, at least one way of doing it. And as I said, we weren't the first to think about a Ricci flow for networks, and we are not the last. So keep working on that. So by now, my own stuff might be archaic. I don't know. So this is how the Ricci flow equation looks. The standard one for smooth manifolds. Gij is the metric. So this is a Ricci. The matrix of the metric evolves with the speed of the Ricci given by Ricci curvature, but it's minus sign. When you discretize it, you take, of course, finite differences, and you get this expression. And so this is a new curvature, new weight opposed to the old one. So here gamma is the weight. I don't know why now. What I should say is that is a big difference between this one and this is something people miss, but that's what makes the discrete flows good ones, I would say. This is a PDE, and PDEs are notoriously hard to handle. This isn't, once you do the discretization, this is an ODE, and as such, it has a reverse flow also, which is not something to be ignored. Okay, so it's much, much easier to gain two things with one stroke. And if I can reserve the moment to boast a bit, so all this Olivier Ricci flows use the scalar curvature effect. They are not proper Ricci flows. They are Yamabe flows formally. So what we did is proper Ricci flow in the sense that it involves the edges and not the nodes. Okay, so you can look at it because it gives different snapshots of a system at different points in time. And you can then faster or stronger focus on the interesting regions. And you can use it therefore for change detection. In the beginning, we worked on imaging with people from the tech. And I have some results, but I focused on networks here and show you perhaps. So this is the scheme which we with Melanie. you put a network, you put some weights, you have the correlation matrix, you do the flow, and then some weights become very, very small. They get under a certain threshold, and then you delete them. And the results are something like this. So these are two peer-to-peer. It's a Nutella network at different points in time. How can you compare them? Okay, but if you use the flow, you can force the evolution in the direction of changes. Yes, if you remember, you look at big changes in time, so then you get something like this. So you can see the points where something big happens, not just some accidental additional disappearance of people on the net. Okay, so let's go back to the brain networks. So we have these edges, connected internodes, these clusters, long connections, but it's very hard to see everything, yes? Now, if I take this apart, then you have to guess what, it's not that easy. So there are two ways of looking at it. You can do thresholding. You can choose the heaviest nodes and edges, that then it's also not very clear. And then you have two ways of going around. One is to go to smaller networks, to do stronger thresholding or to take in smaller portions. And that's nice to have this. You see the backbone of the network, the main transportation information avenues, the network. This is again for the brain human network, but they're small. And the other idea is, and then you can see this again, these bridges and connecting them. This black backbone. By the way, backbone is also, you can use Olivier curvature for detecting that also. But if the network is big, this is not good enough. So then you can use the reverse Ricci flow of which I talked and emphasize the region which are bad or important, so on and so forth. And that's how we did it. And I have some results, but I think one can do much better. So one small example with Melanie is this one. And of course, these small examples are good for something because always you can understand there is a connection between these two. I would expect it more between Jean Valjean, but whatever. But it's a bit too small to convince people from other fields. On the other hand, if you look at the connectome here, we try to embed it, but it turns out, at least at that point in time, there were two models of the brain freely available of human brain. Freely available on the web, the internet, and we chose the wrong one. So it looks something like this. So so this is original network. We try to place the nodes on the brain. So after one iteration, two iterations, three iterations, you see that it simplifies enormously, and you can better see the main connection. But of course, one should do much better than this. Again, we didn't. It's a pity. It's a sad project. Okay. So now it's time to go back to Forman. As I said, I already dropped this line that, okay, you can do Forman for graphs of Forman triangles, for instance. And of course, we have to go back if you want, because as I said in the beginning, it's not important just the connection between two people, but between groups of people. Not just two proteins or many proteins, so on and so forth. So then you are going back to study. How much time do I have? Okay. Okay. So we go back to CW complexes. So we are going back, yes? So this is a Hobbit. This is something that most people have read. And why the Hobbit? Because the subtitle is There and Back Again. Yes. So we are back to Forman. Okay. And the trick is, And this is a nice thing. So you have these horrible curvatures and you have higher dimensions, but Forman curvature is a curvature of edges, yes? It lives only on edges. On edges. Edges are the common border or frontier of two simplices or two faces, yes? Therefore, it doesn't matter how higher dimensional structure you have, you only have to go to the two skeleton. So the two skeleton prescribes Forman curvature. So you have, honest to God, two-dimensional objects, albeit they might be horrendous in structure, yes? And a lot of holes and stuff like that. And again, that's Ricci doing, and he's right in doing these kind of comparisons and to see how good this new curvature is when you add faces. So green one is proper one-dimensional Forman. The yellow one is when you add faces and so on and so forth. So this is a set story which it's time to say it for everyone. So Forman curvature, as you remember, is defined for general complexes. In practice, as you have seen, for instance, in persistent homology, people use simplicial complexes only. Also, from the computational viewpoint, even I, who am far from being a computer scientist, understand it's far easier to determine the triangles in a network than pentagons, for instance. Yes, algorithm is much simpler. Therefore, in practice, moreover, when we did this, there were very few people who were thinking about looking at something more than edges. Ginestra was one, Ginestra Bianconi. So she did something with simplices, and so we did. So in that paper, we said, okay, we can do it theoretically with everything, but in practice, we restrict to simplexes, to triangles only. And we call that the augmented Forman Ricci curvature. And that's what it got wrongly cited. We never said that it works only for triangles. Just this implementation was for triangles. And by now, nobody would believe me. Anyhow. So you see it's much better than other things. And so you compare it Forman, augmented Forman, Olivier, Ricci curvature, and between us, whatever. Okay. Okay, so now I'll do a bit of mathematics. Or at least talk about it. So let's go back to Forman curvature. What's good about it? It's very easy to compute. Even a child can do it. So a smart child. It satisfies some deep geometric algebraic properties like a Bonnet-Myers. It connects between positiveness of Ricci curvature. It discretizes classical results from Riemannian geometry. Positive curvature implies finite diameter, implies finite fundamental group, connection with a dimensional homology group, stuff like that. It's very deep. And for a practical viewpoint, as I said, here it is. And it comes coupled with a Laplace. In fact, with a couple of Laplacian in any dimension. So it's very practical. In a sense, you can do it for filtration, you can extract eigenvalues, you can do anything that you can do with a Laplacian, but with many Laplacian and many scales, so to say. And also, if you have a Laplacian, then you can sell it to electrical engineers, because they know. Okay, so they hate you for that, but at least you can do it. But what's a minus in this thing is that it doesn't satisfy the basic relation which connects topology and geometry, which is the Gauss-Bonnet theorem. So you know Gauss-Bonnet, should I write it on the blackboard, or is the integral of curvature is 2 pi? It's a beautiful thing, and of course, for surfaces, it's very nice. And you have, so for surfaces, the genus prescribes the curvature of the other way around, as you want to look at it. In dimension 3, the result is very different. There is a classical result of Locamp. It's a proof which is elegant and uses Gromov's H principle, which shows that any free manifold carries a metric with negative Ricci curvature. There is a newer proof a few years back of Benedetti, much shorter, but I can't remember now the gist of the proof. So what Forman showed in his paper is that what happens in dimension 3 for proper Ricci curvature for smooth manifolds happens in dimension 2 as well. Any surface has a triangulation with negative Ricci curvature. So once you have two surfaces with negative Ricci curvature, i.e. negative, basically negative Gauss curvature, this violates the Gauss bond. So it succeeds extremely well at the level of functions because it started from there, Laplace, and it succeeds very, very well on the algebraic, topological algebraic level as well because its constructed is defined using algebraic tools, but it fails miserably at the basic Gauss-Bonnet level. Yes? There are two versions. One, in this sense, I just said that it has finite diameter and there's a connection between them. And there is another layer which says that the ones who have positive curvature, they have the same name, but perhaps not the same people use the same name. The second name one says that positive curvature implies finiteness of the fundamental group. It makes sense. Again, think about. Okay, so this, it does very well, but Gauss-Bonnet doesn't work. So there is a solution which was proposed by Ethan Bloch, which is less known result, but is very nice. He does the following thing. He does some modification and he defines some new curvature functions for each dimension 0, 1, and 2. It's only for two manifolds because the problem is there, yes? For surfaces, so to say. But you have three new curvature functions. And it turns out that which are defined in very, I won't bother with them. They're defined in a very combinatorial way. Not very nice, doable for a computer scientist in practice. But when you look at these curvatures, these two don't mean that much, but it turns out that at least for polyhedral complexes, R1 is just Ricci, Forman Ricci, combinatorial one. Therefore, so this is important. You have three new notions, which one of them is an old Forman curvature. So it's for, of course, this holds only for combinatorial weights, but since we are looking at the topology, that's okay. And then you have this relation here, which connects the three curvatures with the Euler characteristic. And of course, you can substitute instead of R1, Forman Ricci, and you have this relation. So we have a Gauss-Bonnet. So this is a, okay, so there is some, okay, exactly like in Forman's original definition, in Bloch's choice of the curvature functions, there is some, you have some choices to make. You can define them in a number of similar ways. So there is some choice. But let's settle for one of them. And then you can go, okay. So now you go back, you can define what is called prototype networks. What does it mean? That means that you go back to the classical Ricci flow. So what happens is that if you have a surface evolving by the Ricci flow, if it's homotopy type of a sphere, it will evolve to infinitesimal round ball and then disappear. This is not something which you want with real life networks to disappear. Then you introduce this mitigating factor, this mean Gaussian or Ricci surface. This is Gaussian curvature, which is It's just a mean curvature, and this prevents this collapsing phenomenon occurring. So, but of course, having this thing here is having the Euler characteristic, yes? Therefore, that's not a big problem. You can discretize it. Instead of mean curvature, we have the mean Ricci Forman curvature, which looks like this. It's number of one faces, edges. And then we have some results, okay? Huh? Oh. Okay, so now we have a definition of prototype networks. I wanted to call them model networks, but it turns out that the name was already taken. So you call a network or two-polyhedral complex spherical. It has positive curvature, Euclidean if it's zero, Euler characteristic, and hyperbolic if it's negative. So we can classify the networks, and then we could expect the flow. If you remember, you have a flow, and we will set the flows to evolve to the model surface, to a sphere in the case of positive curvature, and so on and so forth. So this is a way of doing it. But of course, when you work with Euler characteristic, it's not our main player. And perhaps it's hard to compute. So we look at Ricci curvature, and we'll say that equivalent is that a network is spherical if Ricci is positive, Euclidean if Ricci is zero, and hyperbolic if it's negative. And let's see how it looks like. So we don't have a theory for that. We have a nice definition, but we have some results. So let me show you some results. So this is a hyperbolic network. How do I know it's hyperbolic? We computed curvatures, and the sum is negative. So let's take a few iterations. 3 iterations, 4 and 5. So you see, we started with this one. You know, it looks kind of round. You don't know what its shape might be. But only after 5 iterations, it degrades very much, but it's almost tree-like. So it's almost ideally hyperbolic. Let's do the same thing for a spherical networks. This is a spherical network, I know, because we computed curvature, but it doesn't look spherical at all, yes? So let's evolve it. 3, 5, it's almost spherical even in distribution. So it seems to be very effective. So this is another example. We see the windsurfers social network. So you see how it evolves after 5 iterations. And you can see that things that we had a lot of negative edges here, negatively curved edges, but they disappear after a few iterations, and it shows its true spherical nature. Okay, so I don't know how do I stand with time? Well, okay. We have a day for questions, so I ask myself a few questions tomorrow. So here is, remember I mentioned you this chemical reaction networks, which you can look at hypergraphs, bipartite graphs. So this is a reaction, takes 2 substances to 2 more substances, butane and oxygen to CO2 and I don't know what, and water, for instance. So that's how it looks like. So we computed a few of these. These are hypergraphs. So we computed some. This is another one, E. coli. You can see the humps in these hypernetworks, very simple ones. And this is one of semantic networks, which we use for psychology to see how people. You test for diseases, let's say, by looking how people navigate through lists of words. Nouns. I'm just not getting into details, but I'm just saying that you have use for these higher dimensional objects. And this is, you saw these pictures before, if you remember. And this is what we did with Kevin and Romain. And it turns out it's good. For instance, this is, we compared Forman curvature with classical differential expression. which is something biologists use a lot, and on determining genes which are carcinogen, which produce cancer. And please look at the numbers. So this is classical differential expression, the yellow ones. These are genes discovered using Forman 1. These are genes discovered using Forman 2-dimensional. And as you can see, each of one separately is much, much stronger than classical differential methods. Biological methods, I should say. So this is something which I'm happy of. But of course, again, here we could use only triangles, I think quadruples, but higher dimensional faces, I said there can be 60,000, order of 60,000, we could. And I don't know if they're worthwhile. Okay, you are all tired. And as I said, we use it for this. Okay. So some conclusions, and that means that I'm almost finished. Perhaps next time we'll use the air conditioner. I can't take a nap while I'm sitting, but standing, but otherwise I think it's hard for, I mean, it's not just me. I'm just trying to say that it's not just me. The reason of your being tired. So what I can say about Forman curvature, it's a very nice tool in the intelligence of complex networks. It's simple and efficient. It's an edge measure, therefore it's much better than the old node measures. It's very malleable and versatile, and I skipped through many slides just to show you how many implementations you can use. Autism and intelligence and what, I don't know. Post-traumatic stress disorder, was with the names. You can extend it, not just that you can extend it, it's natural. In fact, you define it by restricting to dimension one, something which is naturally defined in higher dimension. Therefore, you can apply to hypernetworks naturally. It has a natural flow, Ricci flow. It comes coupled with a Laplacian, where not a Laplacian, many Laplacians, pair of Laplacian in all dimensions. Allows you for networks classification through this genus stuff. And it captures the topology, the pi1 and homology one. And therefore, I hope you'll buy a few Forman curvatures. I think that's it, yes. Thank you so much.